Page number 2 in your packet is we're going to just kind of quickly go through what we had talked about yesterday. When we did our coin tosses yesterday, we said that getting heads was a random variable because we had varying amounts of heads from person to person, okay? And that number of heads you got couldn't be predicted because we were tossing the coin and it was a random result. So that is why it was called a random variable. There were 2 kinds of random variables. They are discrete or continuous. Which one was ours an example of, discrete or continuous? Our coin tosses were results were an example of discrete. Why?
They were whole numbers.
Okay, they were whole numbers. They were correct definition is they were a countable number of distinct possibilities. You could in the end you could have 0 heads or 1 heads or 2 heads or so on up to 30 or 20 heads, okay? And so we had discrete random variable. All right, and then we had gone through these ones yesterday as well. So let's take a look at, let's review that other little activity that we did, which was when I had given you a $5 bill, and then we were betting. So let's fill in our results. Remember, the X is the possible winnings for Miss McClellan, and you give me 5 to play, and I get to keep it because if you get something else. How did we do y'all's yesterday? Oh, we started off with the negative. Okay, so we'll go ahead and do that. So let's say that you pick the ace of hearts, then you give me 5. I have to give you back $100. So I lost $95. How frequently did I lose? Will I lose $95? 1 out of 52 because there's 1 ace of hearts and so on. The next one was the other aces, and there are 3 of them, and that's 5. I give you back 10, so I lose 5 times $5 if somebody gets another ace. And then, as just a review, because I got to fill in this chart for us. The other one was the other hearts, and how many other hearts are there? 12 left, and that's you give me 5, I pay you 5 back, so I have broken even. Okay, so I had a profit of 0, and then finally you give me 5, I give you nothing back, so I have made $5, and that's the rest of the time, and that is the 36 remaining cards out of 52. So yesterday we had gone through and we had done, let's see, I'm going to pull in a picture. We had gone through and we had done this problem here, which that's what I just was putting out there. And we went ahead and we did this formula. Okay, so we did this formula where we were taking X times its probability plus X times the probability plus X times the probability. So we were adding all of the X's times the probability. So we found that average was $1.35. And that's where we ended yesterday. So let's go from there.
It seems so low, though.
Now that's on average per person. That's on average per every person that plays this game. So let's interpret this result. And here it is. This means that in the long run, per the law of large numbers, in the long run, each time this game is played, McClellan will make $1.35 on average. So every person that plays, on average, I make $1.35. So even though it freaks me out a little bit that I could possibly give back $100 and lose all that money, do I want to keep playing this game? Yes, I want to have people play this game, come play the game. I'm going to advertise. I'm a casino. I'm going to advertise. Come play the game because I know in the long run that these probabilities will hold true and I will make $1.35 per play on average. What tells me that these probabilities will hold true and come out in the end? The law of large numbers. LOL hashtag tells me that those probabilities will come true in the long run. Okay, so now we did not do the standard deviation for yesterday, and so that's what we're going to go to right now. Okay, so that thing right there is stuck on. Okay, so here we go. So we're going to find the standard deviation, and the formula for that, which you have in your notes, but I've now kind of, let's see if I can move this around. Haha, there it is. So here is the formula. The formula is actually for variance, and variance is the standard deviation squared. And so, of course, this sigma means to do what? Sum. Very good. So that sigma is going to tell me to sum. And sum up all of the x minus the means quantity squared. So you take each value minus the mean, which in our case, what's my mean? $1.35. Okay? My mean is 135. And then, so this is that difference, quantity squared times the probability of that happening. So let's write that out, and then we'll compute. So here we go. The variance. Okay, and let's look back up here. I think when you guys wrote your results yesterday, we started back over here. Didn't we start over here with the negative 95?
Yeah.
Yeah, that's how we did our table in class yesterday. Some of my classes I did it this way. Then by the alls I started switching it around. So whichever way you do it, it doesn't really matter which comes first. You pick an x, and let's go ahead and do what you did yesterday. You have negative 95 minus the mean, which is $1.35, quantity squared times the probability. And the probability of me losing 95 is 1 over 52. Okay, that's the first one. Now, sum that with the next one. What was the next one we wrote? The other three aces. So that's me losing 5 minus the mean quantity squared times the probability. Plus the next one. What's the next one?
0.
It's me breaking even though, right? 0 minus the mean quantity squared times p. So that's the process. And the last one is 5 minus the mean quantity squared times p. Okay? And I'm going to tell you that that number comes out to be 190.5. 190.5. Is that the standard deviation? It is not. That is not the standard deviation. How do I get the standard deviation? I'm going to square root that 190.5, and that comes out to $13.80. So that's the standard deviation, and $1.35 was the mean. Okay? And so now I'm going to bridge this into our favorite thing, the normal model. So let's now connect what we've just done to the normal model. Because let's write what we got. We know we have a mean of $1.35, a standard deviation of 1380, and so let's draw the normal model out. Okay, so here we go. Where is my picture centered? On average, what will I make per play? $1.35. Okay, so my center is going to be at $1.35. How many standard deviations do you draw up? 3. 1, 2, 3. How many standard deviations do you draw down? 3. Okay? All right. So how do I find out the value at this next standard deviation up? Good. Add 1 standard deviation, which is 1380. That gives you 15, 15. Now what? Add another 1380. And that gives you the next one. And so let me go ahead and give you those numbers so you don't have to do that arithmetic. I have that pictured out here. Let's see. Okay, so here are the results. Of course, again, it is centered at $1.35. And as you go up, the first one's 15, 15. 2 standard deviations is 28.95. 3 standard deviations up 42.75. Now, what kind of profit will I have per day on average if I break even? If I give out the same amount that I take in, what will be my what's that number for my break even point? $0. So keep that in mind. Let's go ahead and draw that line in there because we're going to be discussing this line in a minute. So keep in mind that a break even point is when my profit is 0. All right? Now, how do I get these numbers over here to the left? Subtract 1380 from $1.35 and you end up at $12.45. Subtract another 1380 and you're at negative 26.25 and finally negative 40.05. Okay. Now, I need to make myself a note because I should add this problem in next year, but I want to do an extension problem that you don't have written on your paper, so you can write this in if you want, but you don't have to. So either way, whichever you need, but you will be doing problems like this. So take a look at this extension question right here. What is the probability that McClellan will break even or even, oh, you know what? Sorry, these are supposed to be lose money, not loose money. I'm going to lose money, not loose money, by the way. Sorry. What's the probability that I will break even or even lose money? Well, on this curve, I am losing money in this section to the left when my profits are negative. Doesn't that seem natural? When my profits are negative, that's where I'm losing money. So if I want to know how frequently I will lose money, I should use the normal model and compute this area. Okay, so what do I have to do to compute that area with normal stuff, normal curve stuff? Get a what first? Z-score. So here is my Z-score. X is my $0 minus the mean over the standard deviation. And that gives me this Z-score of negative 0.0978. And then I want to find the area below that. So do you recall that? That's when you norm CDF from negative 99 up to that point, and I get 0.461. You know what that means? 46% of the time, you know what happens? By the end of the day, I am averaging a loss per person. 46% of the time, I'm averaging a loss. Well, that's a bit scary. That's kind of, don't you think that's kind of scary? I'm thinking, holy cow, that seems like a lot. 46% of the time, I'm going to be losing money. But what's the flip side to that? Yeah, 54% of the time, I'm going to be what? Making money, and I'm going to be making money more frequently than I'm losing money, so I'm good with that. And how do I know that this 46% will hold true? Law of large numbers. Yes, tells me that in the long run, after days and days and days and days and days, 46% of them will be losers and 54% of them will be winners. Okay? All right, so casinos bank on that. Casinos count on having that probability, and they count on the law of large numbers holding true, and that these probabilities come through in the long run. Okay, very good. So let's now go on to the next thing, which is, so basically I've taught you everything I want to teach you on that. And so let's go ahead and now do some practicing. All right, so your next problem. So from now on, I want you to be able to create your own probability model and compute the mean and standard deviation and then interpret those results. So here we go. Our first one to practice is this situation. For each of the following scenarios, let's see. A fair coin is tossed twice. So you flip your coin twice, not just once, okay? X is the number of heads that are observed. So let's write that in. X equals the number of heads when you flip your coin twice. What are the options when I flip my coin twice that I could end up with? How many heads? But I could also end up with 0, and I could also end up with 1. Yes. That's the possibilities that could happen. I could have 0 heads, 1 head, or 2 heads. Good. Now, I'm going to draw a very simple sample space of the possibilities. Here are all the possibilities. There's just 4 of them. So, this second row is the probability of getting those results. How frequently will I have 0 heads when I toss those 2 coins? How frequently will I have 0 heads? 1/4 of the time, that's right. Here is the case when I have 0 heads. So 1/4 of the time. And the law of large tells me that in the long run, that is the percent of time I will have 0 heads. How often will I have 1 heads? One of them will be heads. 2/4, or in other words, 50% of the time. The law of large numbers tells me 50% of the time I will, oops. So last thing, how often will I have 2 heads? 1/4 of the time, okay? Now, I want to remind you something, just kind of throw in a little factoid right here. Look at these numbers, 1/4, 1/2 of an 1/4. What do those add up to? 1. A probability model always totals to 1. Probability model always totals to 1. Furthermore, can you have one of these probabilities as negative? No, you cannot have a negative % chance of something happening. So your probabilities cannot be negative, and they also must always total to 1. All right, very good. So let's go ahead and calculate our expected number. Tell me expected number. Expected value. It is the mean expected value. It is the mean expected value. Let's see if I know it. It is the center. Yes, indeed. Yes, indeed. It is the average, the mean. Okay, so there you go. Not so good yet. I just figured it out at lunch. Moving on. So the formula that I want you to write out is on your formula chart, and it's this: summing up the x times p. All right, so let's...
Is there any way to write that without all those letters and stuff? Because that's just...
No. That's why I'm teaching you how to read it and to understand what all those symbols are. Okay, x times p. So I'm doing x times p. That's easy. So my first one is 0 times 1/4 plus, what's my next? X times p. What's the next x times p?
1 times 1/2.
1 times 1/2 plus, what's the next? X times p. 2 times 1/4. And that's actually quite simple math that I could even do in my head. That's 1. So on average, I know that in the long run, I will get 1 heads out of the 2 on average. Okay. And now, let's do the standard deviation. I'm going to have you write it out again with the formula today on this problem. But then after that, I won't ask you to write out the formula when it's very lengthy and there's a lot of parts to it. I want to see that you can do it, and I'll just have a couple of parts to it. So let's do this. Here's the formula. The variance is summing up x minus the mean quantity squared times the p. X minus the mean quantity squared times its p. So let's see how that looks. Okay, so here we go. So what's the first x? What's the first x?
0.
0 minus the mean
It's just 1.
is 1. That's what we just figured out a minute ago. X, 0 minus 1 quantity squared times the p, which is 1/4. Okay? Plus the next one. 1 minus the 1 quantity squared times the probability. And then 2 minus the mean quantity squared times the p. Very good. And so I am now going to stop at this point because honestly, it gets very tedious. I mean, you could go ahead and compute this by hand, but I'd like to take a moment and teach you how to do this in your calculator. So get out your own graphing calculator, and if you don't have one, go get mine and do that now. All right, so we had we discussed how to do this in your calculator, so let me remind you that in your calculator, if you're doing this, you are doing one variable stats. That's the under stat calc of one variable stats of what, guys?
List 1.
List 1 with list 2's frequency. Okay, and it should make sense that this is the frequency because I know 0 heads will happen 1/4 of the time and so on. So this is your frequency that you put in L2 and this is what you put in L1 and so on. So we ended up, when we computed that, our calculator gave us that 0.7071, which we had to backtrack and square that. So if I squared it, then I got my variance of 0.49999, I think. Okay, done. So that's how you can do it in your calculator. Hopefully you understand how to fill in the formula because I want you to understand that formula. And so let's go ahead and go on to the last one that we're going to do right here. Oh, by the way, this picture is just showing you that 0 happens 1/4 of the time and 1 happens 1/2 of the time and 2 happens 1/4 of the time. Notice it is unimodal and symmetric. Okay? So, interesting that that's not a coincidence there. All right, number 2. Here we go. Here's this situation. You are going to roll a pair of die. And X is going to be the sum of those 2 die. So let's go ahead and fill that in right here. X equals the sum of the 2 die. And of course, down here, we will find out the probability of getting that particular sum. The probability of getting that sum. Now, question, we talked about this yesterday. If you roll 2 die, what are the options for the sums that you can come up with? Yeah, you could get a sum of 2. In fact, I need to teach you how to interpret this little. This is the sample space. Let me show you what this means, or else this looks very strange. Do you see this 1, 1? That means the first die is 1 and the second die is 1. So what's the sum of those 2 die?
2.
2. Okay, another example. Look at this one. 5, 4. The first die is 5. The second die is 4. So what's the sum of those 2 die? 9. Okay. So I just wanted to teach you how to read that. And of course, you can see here, if you roll a 6 and a 6, what's the sum of those? 12. So we know that our possible sums are these. All right, next question. See this sample space? How many different arrangements, how many different arrangements of those die can occur? How many different are listed out there? 36, correct. This is 36 different arrangements because it is a 6 by 6 square. So that's your denominator for all these probabilities. So go ahead and fill in your denominator for all of these probabilities.
I think that's from the
So I'm going to do the first 2 with you. Yep, so let me do these first 2 with you. Here we go. The first one is, I want to know how many times out of these 36 gives you a sum of 2? How many of these arrangements? Yep, this one and this one only is the only one that sums to 2. So 1 out of 36 is the probability of your die summing up to 2. All right, for example, here's the next one. How many of them will give me a sum of 3?
2.
These 2 right here are the 2 ways I can sum up to 3. Okay, so I want you to fill in the rest of the probabilities. Figure out the rest of those. Okay, so here are those probabilities. So my first question is, which sum is most likely to occur? 7, because it occurs the most, 6 out of 36. Now, have you ever played or have you ever learned how that game craps works in a casino? Anybody? Let me tell you how it works real quick. There's lots of people there around a big oval table. You go up to the craps table, and they're around a big oval table. And they place bets on the number that's going to occur whenever 2 die are rolled. Okay, the sum. So then you get a person who's the roller. The person rolls it. They take those die, they roll it across the table. One of the rules is it has to hit the other side, the end bumper on the table, and then roll back. Okay? So they have to roll the die, it rolls back, and then you look at the sum. Well, guess what? You win unless you crap out. And you will crap out if you get a 7. So if you get a 7, you lose. And you know who wins? Casino wins. So, do you think it's a coincidence that the sum that is most likely is the one that the casino is winning on?
I still don't feel like that's a good enough odds to be put.
What do you think? But in the long run, that'll hold true. And will they profit? Yes. Okay? So see, whenever this happens, when you lose, the casino gets to take all the chips that are on the table and rack them in. Okay? And you crap out and they collect all that money. So anyway, that's interesting. So I want you to go into your calculator. This is too many things for you to write out the formula for. So let's go ahead and have you go into your calculator and determine what the mean and standard deviation are. I'll give you a few moments to do that. Okay, so that calculator, like I said, if you put it in correctly, you get a mean of 7 and a standard deviation of 2.42. So let's do this. This is a new kind of problem. Find the probability that x is greater than or equal to 9. There are 2 ways you can figure that out, and the AP test would take either way. You just have to show your work for both of them because they do come up with 2 different, slightly different answers. So where on this picture chart is that section?
41%.
Nope. See this section right here? That is the section where x is 9 or greater. So what do I need to do with that? I need to add up these percentages. So I need to add up 4 plus 3 plus 2 plus 1. They all have the same denominator of 36. And I think that's 0.27 something. I need somebody to do that for me. That's 10 out of 36. What is that?
It's 27 points, or it's 0.2777.
Okay, perfect. All right. So there's that. Okay, good. So that's one method that you can do this. The discrete, actually binomial method. Okay, so hey, what if I decide to do this with the normal model? What if I decided to do this problem where I take 9 and I want to find this shaded area with the probability of above 9? What do? I find the z-score. What is my x value? 9. So let's do that. Z equals, oh, wait a second, mean is 7, standard deviation is 2.42. So x is 9 minus the mean over the standard deviation. Okay, are you following me on that? Okay, so x minus the mean over the standard deviation, and then what you get on that is, let's see here, if you go calculating that, you get 0.8264. Okay, that's your z-score. But how do I get, that's just the location of this. How do I get this area? Norm CDF from 0.8264 up to 99, that is 0.2043. So 20.43% of the time. Okay? Do you see how these two numbers are slightly different from each other? One's the binomial approximation and one's the normal. AP would accept either way as long as you showed the work. Okay? And so the last thing to tell you is what your assignment is. Your assignment, your homework is pages 6 through 8. And on this assignment, pages 6 through 8, I want to talk to you about just the first one real quick. It says, determine whether or not this table is a valid probability model. Can you tell me, okay, before you pack up, listen up. Can you tell me the quality of these probabilities in order for it to be valid? What should it do? Good. It should add to 1.
That's one.
And not be what?
Negative.
Not have any negatives. The x's can be negatives, but the probabilities cannot. So this first part's asking if those are valid, and then you go to the rest of those. Look, then you start filling in your own tables and figuring out your questions from that. So, again, homework, pages 6 through 8.